Okay, welcome to, what is this? Lessons from Sharding Solr at Etsy. So first of all, so we're going to talk about Solr sharding. So who here runs Solr with only one shard, no sharding? Okay. How about 2 to 10 shards? All right. About 11 to 50. About more than 50. Oh, wow. Okay. All right, good, good. So who am I? Why am I here? So I'm Gregg Donovan. I work at Etsy, and been working on Solr and Lucene at Etsy for about 5.5 years. Before that, I worked on Solr and Lucene at theladders.com. I've spoken here in 2011 and 2013. You may have attended my 90-minute session on garbage collection in 2013, and I apologize if that induced a coma. So that's a lot of time working on search. Why would I want to work on search for so long? These are some slides from Jeff Dean at Google on building large-scale information retrieval systems to talk about why you might want to work on search. Search is a wonderful blend of distributed systems, algorithms, machine learning, UI. Small teams can build systems that are used by many, many people. This slide is kind of old. You can see it says hundreds of millions. Of course, now it's billions. And the challenges increase with how many documents you have, how many queries you do per second, the latency you require, how much information is in each document, and how complex your scoring and retrieval algorithms are. And so the difficulty of the engineering is roughly equivalent to the product of all these different parameters. And I would add 2 other challenges that are relatively new, or people's expectations of search keep growing year after year as search keeps getting better. And mobile performance. If you want to get a 1-second round trip time to a mobile device, you got to assume about 900 milliseconds of that is going to be rendering, network time, et cetera. So you've got about 100 milliseconds to get a high quality response to a mobile device. So what is Etsy? Etsy is the marketplace we make together. It's an e-commerce platform for sellers of handmade and vintage goods. We're headquartered in Brooklyn. We have 1.5 million active shops, 32 million items listed, and almost 22 million active buyers around the world. So the agenda, we're going to talk about different generations of our sharding infrastructure at Etsy, starting with not sharding, which we kept going as long as possible, and then what we call local sharding, and then distributed sharding, which is what most people think about sharding and what we're about to launch. So I'm trying to focus on the stuff that's mostly more generalizable. So V0, not sharding. So let's go back to why we would shard in the first place. Your data size grows beyond the RAM that is on a single box. Lucene can handle this via disk, but there's a performance cost. The data size could grow beyond the disk, the local disk, or you could just have latency requirements that require you to throw more CPUs at the problem. So we put off sharding though as long as we could meet our latency requirements, just to keep the system as simple as possible. And so we kept the data size small by not storing anything other than IDs. So our queries look like fetch a primary key, fetch a foreign key, get the score. And the fully materialized, denormalized objects that we're searching for are in memcache. And so we just really return these basic things from search. And we only index the fields we really need to index. Once we finish experiments, we prune out any fields we are unused. And then we just also buy more RAM for the servers. And that kept us not sharding for quite a while. And it was great because it let us focus on other things. So here's an ugly diagram of roughly what that architecture was. So we run a LAMP stack. So we've got Apache and PHP, talking Thrift to a single 31 gig JVM that handled query generation, basically taking Thrift parameters and turning them into Solr J queries, which hit an embedded Solr server that had every type of search index that we had. And then at the end of it, we would do some re-ranking and diversification that I'll maybe talk about a little bit more. And that was it. And that got us through a number of years. And so this fails in certain ways, garbage collection being the big way. And garbage collection was sort of our big bugaboo for years with this infrastructure. Eventually what we came around to, and so garbage collection, the problem is not just being natural garbage collection that occurs because you have a high throughput system and Solr sort of segmented architecture with a lot of caches being loaded and unloaded. So there's a certain amount of natural garbage collection. And there's unnatural garbage collection that comes from programming errors. And so we wanted something that was resilient not just to regular memory problems, but human-induced memory problems. So we came up with something called the Banner protocol. We have a client-side load balancer that connects to a server. So we've got a pool of servers. It connects to one server. It waits, say, a millisecond or 10 milliseconds for a 4-byte header, 4-byte packet to come back from the server. And then once we get that, then send the query. And that sort of indicates to us that the server is live and ready to receive queries and process them effectively. So if we didn't wait, we might connect to a server, send the query, have the OS accept the TCP connection, have the OS accept the bytes, but it might be in the middle of a second-long garbage collection and do nothing. So this helped us avoid a lot of GC problems. So that's sort of basic resilience with that system. Eventually, we wanted to increase our latency. We didn't want to deal with such big JVMs. A 31 gig JVM is a real pain in the butt to open up a heap dump of and analyze memory problems on your laptop. And so it's very practical. And so we thought, OK, we want this to be faster. What's the simplest thing we can build? And so we came around to this idea of local sharding. Can we just make better use of the single machine that has all the data? And one thing you'll notice if you send an expensive query to Solr, and let's say it's a 40-core box, and you can watch it in HTOP, and only one core will be busy, no matter how complex the query is. So we looked at different ways to speed this up. Segment-level parallelism was one idea we explored, and Shikard, Etsy worked on this. So this is basically searching all the different segments in parallel. And this works pretty nicely, but there's some overhead, some concurrency overhead to it. So what we eventually ended up with is splitting that big 31 gig JVM into 8 smaller JVMs, all on the same box. Made a separate process that does the re-ranking, query generation, has SolrJ, and then does the re-ranking once we get it back. We call it the mixer. So it sort of mixes up the results. And based on Solr distributed search, not Solr Cloud, although this approach would probably work fine with Solr Cloud as well. And we made a few tweaks. One is that by default, Solr does a 2-pass distributed search. The first thing it does is it gets the top IDs. So it sends your query out, and it just retrieves the IDs of the top scoring documents. And then it goes back to all, then it does a merge, and it looks at the top K, and it goes back out to the shards and says, give me all the stored fields that are required for the IDs that are going to be in the final result set. So for us, because we're only really fetching a primary key and a score and a secondary key, the 2 phases didn't make a lot of sense for us. It was just another place where things could slow down. So we implemented a single pass mode for Solr, which doesn't make sense if you have, say, a lot of stored fields that are expensive to fetch. But if you don't, this worked quite nicely. We added some tracing via HTTP headers, so we could pass a UUID and some other metadata through all the different shards. And let's see. So another problem we had is that we're fetching a lot of documents from every shard, because we do a lot of re-ranking once we get these things back. And we use Solr's field syntax to speed this up and fetch the data from the field cache rather than off of disk. And so if you do this field syntax there, that will cause it to go to the field cache and never hit disk and always just fetch it from memory. It will require it to use the memory required for the field cache, but if you're sorting by this field, you're already using that anyway. And we also worked on another patch to make sure that when all of these fields are these pseudo fields, so they're not real stored fields, that it never fetches any of the stored fields. So this sped things up quite a bit for us. That was a good win. So the result of this local sharding business is that had a nice latency win. We ended up with a system that was relatively easy to manage. The failures were pretty well understood. Recovery was pretty well understood. The runbook was relatively simple. And we just avoided all of the very difficult distributed systems issues that you have when you're fanning out across your data center. So that got us another couple of years. And we, again, worked on other things. And so eventually, we wanted further latency improvements. We wanted to prepare for our data to exceed a single node's capacity. And to get significant latency improvements, we wanted to use more CPUs than we had on one box. And that required going out across the network and building a real distributed system with real RPC, real resilient RPC. And so, one of the lessons I've learned is that if you're going to do this, the first thing you should do is read everything by Google's Jeff Dean and Twitter's Marius Eriksson, who built the RPC systems at Google and Twitter. In fact, if you want to do that now, my feelings won't be hurt. But I'll be talking about a lot of their papers. In the rest of the talk, I would recommend reading all of them. They're great. So new problems, because we're fanning out across lots of different machines. You could have partial failures. You could have one shard out of, let's say, the 64 shards that we're talking to being down or slow, or just lagging because it's garbage collecting. You need to synchronize the cluster state and configuration among all these different shards. You have to deal with network partitions. I'm sure you guys have heard of Jespin by now and all of the network partitioning testing that Solr Cloud and Elasticsearch have gone through. And now all of a sudden you have to deal with distributed IDF and the issues that causes for ranking. So what is distributed IDF? So Solr uses TF-IDF. I guess we're moving to BM25, but they still have the IDF, inverse document frequency. So how often does a particular term, how many documents does a particular term occur in versus the size of the whole corpus? When you shard things and you're using local statistics, you might have very different local statistics, or even just slightly different local statistics might mean that one shard is favored in your result set over all the other shards. It might bias your result set. So Solr has their own approach for sharing the statistics when you're fanning queries out. We didn't end up using that. What we did is we calculate the IDF offline in Hadoop. We ship that data set to each of our Solr shards. We have a custom similarity factory that has a cache of basically term to score, and we override similarity factories, explain methods to provide this instead of the local index statistics. And when we have cache misses, what we're working towards is if there's a miss, if there's something we don't have in this Hadoop generated data set, it probably means it's pretty rare, or it's a new term, it only shows up a handful of times. So to smooth out and even out the IDFs across all the different shards, we just give it a constant representing, hey, this is a rare document. And IDF doesn't have to be exact, but if you can get it to equalize on all the shards, it smooths out all these ranking issues. And one thing we've thought about is extending this approach to potentially solving some of the issues that happen with internationalization, where you might want the same IDF score for jewelry in English that you have jewelry in French. And if you're doing this offline, then you can solve that sort of problem. So distributed sharding. So Solr's abstraction for sending out sharded queries is the shard handler. And right now it ships with an HTTP 1.1 based implementation that uses the same querying that SolarJ has. And it sends one query out with, or SolarJ will send a query out with distrib equals true, and then the shard handler will send it out with distrib equals false, and then aggregate all the results. And if you're sending out to say 100 different shards, by default, it'll send out the rows, the number of rows that you requested overall to each one of the shards to make sure it has a globally accurate ranking. You can adjust that if you don't need it to be perfectly globally accurate, and take down the number of rows that you ask for. And that makes the computation a lot easier on the system. So we started looking at Solr search handler, and it's based on HTTP 1.1, which has some problems. There's head-of-line blocking with HTTP 1.1. So if you send multiple requests over the same connection, it's going to wait for if you send A, B, and C over this connection, and A is a slow request, and B and C are really fast, you have to wait till A comes back before you can get B and C. So that's not great for RPC. And to work around that, like Solr does, you end up having these connection pools. There's issues where you have multiple connections between server A and server B, and you can have distributed deadlock. So we looked at how can we take this shard handler and extend it and make it a little bit more resilient and a little more performant, and handle things like partial failures, backup requests, a certain one shard out of 100 being lagging or GCing without slowing the whole system down. So the big methods here is it's calling these things from the search handler in a loop and submitting once for each shard, and modifiable Solr params being the parameters. And then when it's done, it calls either this or this, depending on if you're tolerant of there being errors. So that's the basic mental model to have of what's happening. So we looked at that, and then we thought, like, well, we're going to be sending out queries to lots and lots of different shards. How do we understand what's happening in the system? So what we wanted was distributed tracing. So instead of just looking at our logs and trying to figure out what was happening, why was this shard 100 milliseconds slower than this other shard? And rather than just looking at logs, we wanted a tracing system that could look at the whole fan-out tree from top to bottom and record all the events along the way and what was happening exactly. And when you see that, it looks something like this. And this is Etsy's cross-stitch. This is inspired by Twitter's Zipkin and Google's Dapper. And they all sort of work the same. You're measuring these spans where a request goes from server A to server B, and then events along the way. These things get written locally and then aggregated to build these sorts of trace trees. And you can dig into them and analyze, let's say, maybe this thing that's happening linearly could be made concurrent. It gives you a great way to analyze what's happening. So we eventually built this into our shard handler implementation. And some of these distributed tracing systems will even have events like GCs, which are critical to understanding why a particular shard might have been slow. And another great thing when you're doing this sort of analysis is if you're doing Wireshark TCP dumps, is to make sure you have a single UUID that if you're looking at a PCAP file in Wireshark, you can search for it and see all the TCP traffic. We found that to be very helpful. One big lesson for us was to really understand our networking hardware much better than we did going into the project. Because if you're all of a sudden going from a small number of shards to 64, 100 shards or more, you're really increasing the network traffic and putting a much bigger strain on switches and NICs. And so the lessons we've had is to prefer line rate switches. This is if you're actually sending lots of documents. We request something like 1,000 documents from many shards. If you're requesting just a global top 10, it's going to be a lot of connection traffic, but not a lot of packets. But if you have a lot of packets going through, I would look at line rate switches so that they can deliver a gig out if they're getting a gig in, and prefer switches that do cut through to store and forward. That being, they read the IP header and then start delivering the packet immediately to the destination rather than buffering the packet as it comes in. And graph the switch statistics in the same place that you're looking at your search latency. If you're having TCP retransmissions on your switches, that's going to affect search latency. If you don't have those things graphed, you're not going to understand why they're happening. And that's what we did. So we came to this kind of late. But this was a really good lesson for us. And I think one of the reasons we came to it late is because I think as engineers you get so trained to not blame the network after having blamed the network for a software problem like 100 times and having been wrong. So eventually you stop looking at the network and assume it's just working and it's your fault, but keep it in mind. So the first thing we did is the first experiment after testing Solr's default implementation and seeing the limitations around not having distributed tracing, using HTTP 1.1, finding it difficult to sort of figure out what was going on and why things weren't as fast as we were expecting them to be. We built a shard handler, finagle shard handler, basically implementing that Solr API using Twitter's finagle. And we came to this because Twitter has, as far as I can tell, as best I can guess, the most JVMs in the world, and they've built this amazing RPC system, unfortunately in Scala, but the turducken of programming languages. So this is built on Netty. It uses this very interesting MUX RPC multiplexing protocol, which allows things like GC avoidance, where a server can say, I'm about to GC, don't send me any requests for a while. And that's amazing. That's not something you could do with HTTP 1.1. And it's got built-in support for Zipkin distributed tracing. I think its futures-based nature, where you're modeling requests as functions that return a future. So future shard response rather than blocking. I think that's it's a very natural computational model. It's inspired Facebook's RPC system called Wangle. And this is probably, I think, where we're eventually headed. So that was I think it's at this point the best RPC library on the JVM that exists in open source. So it was very interesting to plug it into Solr. Second experiment, we did a custom thrift-based protocol. I found it a little bit easier. To write a blocking API was a little bit easier to grok because SolarJ's API and Solr's API all the way through is based on blocking I/O. So we wrote something with blocking I/O that's sort of a little mentally easier to integrate. Put our own distributed tracing in it. Added some LZ4 compression to try to minimize the network throughput. And basically took the Solr bin format. You guys know what the Solr bin format? Okay. So basically, take Solr's JSON output, and Solr has this custom binary format for that shrinks it down pretty well. So we basically take that, LZ4 compress it, and send it across. So this is what we're working with right now, and we'll probably roll out in the next few weeks. But I think we're probably going to go back to finagle at some point. So I think other future experiments that we were looking at is HTTP 2, and I think this is probably where Solr is headed in the near future. HTTP 2 solves the head-of-line blocking issue. You get one TCP connection that multiplexes different requests. You can have back and forth traffic where maybe you could even build something like the GC avoidance into it. There's some really good libraries, not Commons HTTP that Solr uses. They'll have to ditch that because that's a few years behind. The Jetty client appears to be where Solr is headed as of Jetty 9.3. But this stuff might come in Solr 6 because Jetty 9.3 requires Java 8, and I think Java 8 is not slated till Solr 6. So this stuff might all come at that point. But that's something to keep in mind. If you're doing sharding and you're just going to take Solr's default, this will probably give a big speed bump when it comes. So one thing we did that's a little unusual is we moved an embedded Solr server into our SolarJ. So by default, Solr will have you'll have your SolarJ client. It'll randomly pick a Solr shard to go to. That Solr shard will fan out to the rest of the hosts, aggregate the responses, sort the top K, and then send it back to SolarJ. So we moved that functionality into SolarJ by just making an empty embedded Solr server. It's got a RAM directory with nothing in it. It saves a network hop, and one advantage is that it makes the individual shards a little bit easier to profile and tune. There's not quite as many threads doing fan out. It's sort of easier to look at a URKit snapshot and understand what's happening. And I haven't tested this, but it could be a little easier on the CPU caches to have sort of more homogeneous workload on the shards. So the good things about distributed sharding, the individual shard times demonstrate very low average latency. The overall so out of the box, the overall P95 and P99s were nowhere near the averages. So let's say we're going out to 64 shards, which is what we've tested the most. So why is this? So shards lag due to GC, due to filter cache misses, OS hiccups, networking hiccups. So a lot of reasons it can be a little slower. And the more shards you have, the higher your chances to hit an outlier. Sort of like it's always P99 somewhere in your system. You're always going to hit a P99. So how do you handle that? So one solution, and again, I'm pointing to Jeff Dean, you could just eliminate all sources of inter-host variability, eliminate GC, easier said than done. Make your filter caches gigantic. Of course, that'll make GC worse. Eliminate all OS pauses, networking hiccups, use InfiniBand or something. This is just not realistic. There's always going to be hiccups, and you have to design your system for your host to be unreliable. You might have deploys, restarts, et cetera. So there's two things we've worked on to deal with this individual shards lagging or being non-performant. One way is backup requests. So you have shard 23. You're going to send out send out requests to two different replicas for shard 23's data. Whoever comes first, you're going to use that, and then you're just going to ignore the other one. Of course, that doubles your traffic. So a little less crude is to wait a certain number of milliseconds for shard 23 to come back, and then send a backup request. But what we came around to is a sort of adaptive approach where we send it out to 64 shards. We don't know how long these things should take, so we wait for a certain number of them to come back, and then based on that, we decide how long to wait for the laggards. And we don't do this, but it would be great to cancel the slow ones so that they don't, let's say they're slow because they're GCing, you don't want them to get back to work on these responses you don't care about when the GC is over. But that's a little difficult because it's hard to cancel a Lucene request, but something we've thought about. And then there's good enough. There are certain requests in your system, and we have it with ads, for example, where you don't necessarily need to get 100% of the results every single time. So wait for, let's say, 95% of your shards to come back. Wait a couple extra milliseconds, or don't, and then just return what you have and ignore the stuff that lags behind. There might be cases where it's better to have 95% of your data in 50 milliseconds than 100% of your data in a second. For us, with something like displaying ads, our SLA is very low. So if we have to wait a second for a lagging shard, then we show nothing. So this also introduces some additional problems. Should you cache these partial results? How does paging get affected? But there's certain cases where it works really nicely. How do you resilience test this distributed system? You've got all of these different shards now. So we wrote something called the Troublemaker, actually written by Etsy's Toria Gibbs right here, if you want to ask her about it. It's sort of inspired by Netflix's Chaos Monkey, and it tests all the different ways your system could fail. Simulates, let's say, your SSD breaking, which is the most common thing that happens to us, or networking problems, or a host going down, or a process going down, or a JVM crashing. And you want to make sure humans can operate it, so we do these failure simulations during the day with everybody awake, run through all these different ways that it could fail, and make sure that people know how to handle it, make sure the runbook reflects what you actually want to do when these failures happen. And yeah, don't wait till 3 a.m. All right, I talked quickly, so bonus material, and it's free. So another lesson we had along the way was to make sure you know your kernel. We had a big delay in the project because we dealt with these really weird behavior, dealt with this really weird behavior in the JVM, couldn't figure it out. Eventually, after a couple of weeks, we traced it down to this really weird futex wait bug in the CentOS 6.6 kernel. It was also in a bunch of different kernels. Patches had to be backported. So check your kernels, make sure you're not vulnerable to the futex wait bug. If you've updated recently, you probably are not, but that was a big problem earlier in the year. So one thing we want to do is to make our kernel updates independent of our distribution updates, because those get updated very rarely, but it would be great to have newer kernels. I mean, there's amazing stuff in the 4.x series of kernels around introspection of the kernels and being able to sort of in situ profile what's happening inside the kernel. But that's not going to come to our CentOS 7.1 distribution for years, so we'd like to separate those things. A few other things we're working on before questions. Started to work on Mesos for orchestrating our clusters. We have this very nice system right now where we have a hot cluster and a completely full-sized cold cluster, and we send requests to the live cluster, and we deploy to the cold cluster, and then we switch traffic to it when we're done. It means we have very, very fast rollbacks, and it means we're wasting a lot of hardware. So we want to use Mesos to try to increase our resource utilization, but still having fast rollback and easy deployment. And then we're also kicking around the idea and starting to investigate and purchase hardware for using GPUs. We have got a lot of very computationally intensive projects that we want to work on to improve ranking, and there are GPUs out there with thousands of cores, and so this is something we want to work on. If you know anything about that, please let me know. And if any of these projects sound interesting to you, we're hiring, of course, so come talk to me. Standard pitch. Thank you for coming. Appreciate it. And we have 9 minutes for questions. Oh, yeah. Cool. Yes?
For your GPU ideas, are you looking to simply do that in some of the Solr components, or is it outside of Solr?
Ideally, it would be something that could integrate nicely right into Solr. I mean, I know that a couple of years ago, the folks from NVIDIA were reaching out to Solr committers trying to send them free GPUs if they would work on integrating GPUs into Solr. And there's some academic literature out on it, and I know I've heard rumors of folks doing it, commercial folks doing it in production. I think personalization algorithms that might be for personalized search, where you have lots of different, lots of matrix math, but how to integrate them exactly with Lucene scoring and what happens in Lucene and what happens in the GPU. It's tricky. So, yeah, if you know how to do it, we should definitely talk.
You mentioned that we should all know about the kernel. So I wonder, during the troubleshooting process of your three components, at what point you decided that, oh, I should deal with the kernel function to effectively troubleshoot it?
That's a good question. I guess we've some sort of come to that out of necessity when there's things that we couldn't explain otherwise, where they were failures we weren't used to seeing, where processes were pausing. I think that the futex wait thing really got us because the JVM would pause outside of safe points, which was really odd, and so that got us looking around. But one of the things we want to do is we really want to learn to do is to write something like eBPF, where you can dynamically load introspection points into syscalls and aggregate statistics, and you could maybe count syscalls, change things. But that's sort of on our to-do list. Yes.
So for the offline IDF computation, did you handle the real-time index update?
No. We're not real time at this point. We update the index like every 12 minutes, and this data set is actually updated nightly. So, but we actually build the data set off of more than just the stuff that's actually in the index. So it looks over a longer amount of time at historical data in addition to the stuff that's live. So it doesn't exactly reflect what's in the index, which might not work for some use cases, but for us, where we just need a rough idea of like, is this a popular term or a rare term or a medium term, it works pretty well. Yeah. We did.
When you went to Sharding, did you find that you still needed to transport large indexes?
Yeah, that's a great question. We did, we have this blog post, if you haven't read about it, on our engineering blog about how we used to use BitTorrent when we had this 31 gig JVM and we had huge indices. We used to use BitTorrent to ship it around the data center. At this point, we're back to regular Solr HTTP replication with the shards being small enough, and we also sort of smooth out when things, when the HTTP replication polling happens, so the network's not overwhelmed. I kind of missed it though. It was fun. Yeah. Yeah. If it wouldn't be like a total dump, then we would have. You know, the approach that we took, where it was really deeply integrated into Solr, I'm not sure that was worth the hassle. But if you have a huge index and you wanted to get it to every slave very, very quickly, you know, BitTorrent is great. And there's a Python BitTorrent library that we used just for that that I could email you that I don't remember offhand. That was great.
Similar to the previous question. Like, you have a live collection, but did you have to have a snapshot of the live collection? You know, if you had to have, then how did you copy all the indexes to the each shard to the all the replicas on the
With BitTorrent? Oh, right now? Right now we use HTTP replication in a repeater tree. So we have for each shard we'll have a single master, and then say 5 repeaters, and then 5 below them, 5 below them in a tree. Not Solr Cloud, yeah. We are using neither. We're using Parallel old gen. My last talk, the garbage collection talk, talks a lot about that. The reason we have stuck with it is we found the collections to be predictable and require very little tuning, whereas well, G1, first of all, is the Lucene committers advise against it, and we found a lot of JVM crashes with G1. We found CMS to require a lot of tuning, and then our workload changes all the time. So we didn't want to tune CMS every time we changed things. We also found CMS would get into a bad state sometime where it couldn't keep up, and it would just get stuck GCing, and we'd have to kill it. Whereas Parallel Gen, it does some stop the world collections, but they're relatively predictable, and that the banner protocol actually fit nicely with a system that was either GCing very, very quickly or doing a very long garbage collection to clean everything up. So during that period, we just wouldn't send it any queries. So if there are JVMs that are GCing, we used. So this is actually not something we use in the same way these days. So we have this thing where when we had one big JVM, this worked pretty nicely, where you had this 31 gig heap running the parallel collector, and occasionally it would do like 2-second stop the world collections. So we wanted to make sure that it could actually run Java code before we opened a connection, sent the query, and the OS will of course happily accept your TCP connection, happily accept the bytes you wrote, and then just keep them buffered there for the JVM when it comes back to life. So we wanted to really test if the JVM was alive. So we make the TCP connection, and then we just wait for these particular 4 bytes, which you'll see on our hoodies if you look closely. And getting those 4 bytes, and the very first thing you do on the server is just write those 4 bytes to the client, and then you read the request. And so that sort of proves to us that the server is alive. The server can handle requests. It doesn't protect us from a GC in the middle of the query, but GCs sort of have this Zipfian distribution, and if you've just had a large collection, you're probably not going to have one a few milliseconds later. And if you do, you have bigger problems. Yes.
Have you considered like a service registry kind of based approach, where like all the solar JVMs like register there and periodically renew it, short periods, and based on registry you figure out like better thing like that?
We have a sort of a static cluster mapping at this point, and which happens on deployment, and then that sort of gets r-synced out to every host. So rather than like Solr Cloud has, where a node will register in Zookeeper and deregister from Zookeeper. So we have this sort of static registry that happens on deployment, and then we just have to handle things being down that said they were up. And at some point, I think we'll have something a little more dynamic. Yeah.
What will be interesting is like hack the memory manager inside the JVM, so that like when it goes in.
So we tried that. We tried this thing a few years ago where we wrote some C code to hook into the JVM so that right before it started garbage collecting, we used IP tables to shut down connections from the outside. And that worked really well for large collections, but we found that it took like, I don't know, 10 to 50 milliseconds for IP tables to shut everything down. But you have all of these tiny collections. So if there was a way to do it just for large collections, that would be great. But I think that's actually what Mux in Finagle does in a much more intelligent way is that they're keeping track of statistics in the JVM about collections, about how much memory is used, and they're able to predict the GC ergonomics and predict when a GC is going to happen, and then just broadcast that out to clients. And that seems like a great solution. Cool. So we're out of time, so I have to I guess hang out. What's the thing? I wait outside. So I'll wait outside for questions if anybody has any more questions. Thank you so much for coming. Really appreciate it.